Okay, good afternoon, everyone. Let me start off with this. Let's see, just a few reminders. Okay. Let's see. So let me remind you that assignment 5. Okay, sorry about that. So let me remind you, assignment 5 is due Monday. Maybe to start off today, I'll start off with a quick example. You know, similar to assignment 5. Let's see, there's exam 2. That's on April 7th. Okay. Just posted an announcement for that on Wednesday. Okay. If there is some conflict for you, please let me know sooner rather than later. Okay. So April 7th for exam 2. Let's see. I guess that's it for reminders. So let me tell you the things we want to do today. Just a quick example, similar to his assignment 5. Or I'll just say a little bit about assignment 5. This is weird. Yeah, that seems better. Okay, let's just start out with, then we want to get back into ring theory. Just some basic definitions and examples. Okay. And probably that will be it for today. Okay, so does anyone have any questions about the exam or the assignment? Actually, if you have a question about the assignment, that's the next thing we're going to do. So if you have a question about the exam, you can ask it now. Okay. Okay. Yeah. Oh, someone has a question, maybe? Oh, How many questions on exam 2? I think 4. Oh, how long will the final exam be? I didn't mention yet because actually, okay, let me answer about the final exam first. I'm waiting for the final exam. I'm waiting for the approval of some committee to say how long the exam will be. But however long the exam will be, I'll make sure that it is kind of like a fair number of questions so that it is, you know, it's not unreasonable. For the final exam, actually, I can't just make it how long I want, but the amount of work will be like appropriate for the length of the exam. Okay, and as soon as I find out exactly how long the exam is, I'll tell you. Okay, but if I forget to tell you, you can sure ask on month, keep on asking until in case I forget. Okay, and then the next question is, well, it was already answered in chat, but Chelsea asked, what assignments would coursework 2 be on? And yes, it is assignments 4 and 5. Okay. Okay, I think that I have addressed all the questions in the chat. So I'll move on. I'll just talk a little bit about assignment 5. And the point of this assignment is, to use some of the basic properties of solvable groups as well as the C-love theorems to prove that groups of certain order are solvable. Okay. So for this assignment, we need to know a few facts, which I'll just remind you of. I'll just call them facts. Okay. The first one is that if P is a prime and the order of G equals that prime number, then G is cyclic. Okay, so G is a cyclic. The only group of, if P is a prime, the only group of that order is a cyclic group. Okay, so for example, if I have a group with 5 elements, that group is a cyclic group. Okay. The second point is that any abelian group is a solvable group. So if G is abelian, then G is solvable. Because I just write my series to be like this. This quotient G mod the trivial subgroup is isomorphic to G, and so the quotient is abelian. So this is like this, or said another way, if G is abelian, then its commutator subgroup is trivial, and solvable groups have the property that when you keep on taking the commutators, eventually you get the trivial group. And here you just take the commutator once and you get the trivial group. So that would tell you that it's solvable. Okay. The third point, just says if you take the commutator subgroup a bunch of times and you get the trivial group, then G is solvable. And then the fourth point says that if N is a normal subgroup of G, G mod N and N are both solvable, then G is solvable. Oh, sorry. Okay. And then the fifth point I wanted to mention was that I think we will need for this problem that, right, if G is a P group, then G is solvable. Okay. And our strategy for these problems is to combine the C-log theorems with these properties to prove things like any group of order 12 is solvable, or stuff like that. Okay. So if you need to use any of these properties in your questions, you just say, you might just state the property you need and say like by class theorem. Okay. So let me just sketch out as an example, let's do question 1, and I'll just sketch out a strategy and then you have to come back and fill in the details. Okay, so, and let me also tell you what is the context of question 1. Let me do that first. So question 1 says the order of G is 60, and if N5 is the number of C-log 5 subgroups, and the question is, if N5 equals 1, then G is solvable. And then we showed that, and then we have previously, this is the context, we have previously shown that if N5 is greater than 1, then G is a simple group. Okay. Okay, and then so we can show that this means G is like kind of not solvable. Just I'll do that on the side here. So first of all, G is not abelian, because if G were abelian and simple, it could only be a cyclic group of prime order, and 60 is not a prime number. If G abelian and simple, then the order of G is prime and 60 is not a prime number. Okay, so G is not abelian. And now G is a simple group, a non-abelian simple group. And furthermore, you can say like, look at G prime is not equal to G because, or sorry, G prime is not equal to the trivial group, because or else, if G prime was trivial, G would be abelian. Okay, G prime is normal in G. Now G is a simple group, so any normal subgroup has to be either the trivial subgroup or the entire thing. So that means that G prime has to equal G. So G prime equals G since G is simple. Okay, now when we take the first commutator, we just get G back. Now if we take the commutator of that, we just get G again. We just keep on getting G over and over again. Okay, so G like that. After taking the commutator n times, you just get G. Okay, so in particular, no matter how many times you take the commutator, you never get the trivial subgroup. So that tells you that G is not solvable. So non-abelian simple groups can never be solvable, is what we're saying there. Okay. And it's like not solvable by a long shot, you know, like you take the commutator, you don't even get something smaller, you just stay where G is. Okay. And now what we're trying to say for this question is that in the situation where n5 equals 1, well, then you have, not only is it not, your group is not simple, it's solvable, which is like, you know, if you take the commutator enough times, you get the trivial subgroup. Okay. So let me just sketch out what we should do. Well, since n5 equals 1, we should find a C log 5 subgroup. So let P be a C log 5 subgroup. N5 equals 1, well, that means that there's only one C log 5 subgroup. And so P is normal in G. Okay. Now, P is a C log 5 subgroup. That means the order of P is just like, comes from the factorization of 60. 60 is like 5 times 3 times 4. So the order of P has to be 5. Now, the order of P is 5. That means P is a 5 group, so P is solvable. Okay, and now G mod P, since we can form G mod P since P is normal, G mod P has order 12. Okay, sorry about that interruption. So G mod P has order 12, and question 2 says, all groups of order 12 are solvable. So G mod P is solvable. Okay, now P and G mod P are solvable, so G is solvable. Okay, and that is a strategy for a question 1. Question 2. Oh, someone has a question?
Yes, how come G mod P has order 12?
Oh, yes, this is a good question. So G mod P, that is the group of cosets of P. So there are some different ways to calculate the order of G mod P. This is the number of left cosets of P. Okay, so each left coset has 5 elements. All the left cosets together give you G, which has 60 elements. So turns out the number of left cosets is just the order of G divided by the order of P. That's just 60 over 5. Hopefully that's 12. Yeah. Okay. So the order of the quotient, G mod P, that's just the order of G divided by the order of P. Well, we know P has 5, G has 60, so we just have 12 in the quotient group. Okay, but thank you for that question. Yeah, and then we say, well, question 2 is to prove that basically to prove that any group of order 12 is solvable, which covers this case. Okay, so I hope that gives you kind of somewhere to start for question 1, as well as for like maybe some ideas for question 2. If you need to, maybe remind yourself, like in the notes of the C-lob theorems. Okay. Okay, so for now, that's all I will say about assignment 5. If you're trying whichever question on assignment 5 and you want to send me your ideas, please do that. I will try to respond to you fast. Well, like within a day. If you send me something on Sunday, I'll try my best to send something back to you before Monday. Okay. So I'm gonna leave this part unless you have any. If there's any last questions on assignment 5, please please voice them now. Okay. So I'm gonna move on. We're gonna get into ring theory. Okay, and we have, like, you know, what is the usual example for a ring? It's for us, it's usually the integers. So we have the integers. Well, that's just a set. But the integers, so when we were talking about group theory, we thought of the integers as being a group with addition. And now when we're talking about ring theory, we remember we also can multiply integers, okay? With 2 operations plus, we call that standard addition if you want. Subtraction, or no, sorry, multiplication, standard multiplication. And then I think on Monday, I wrote down all the properties, all the axioms for rings. Basically, you need to be able to add and multiply, and you need to have all these properties. Like you need to have an element 0, the additive identity. You need to have a multiplicative identity. I'll try and write them all down, at least kind of abbreviated. So, you know, there exists 0. So R is a ring means there exists 0 in R, x plus 0 equals 0 plus x equals x for all x. Okay. For all x in R, there exists negative x with x plus negative x equals negative x plus x equals 0. We have x plus y equals y plus x. And we have x plus y plus z is the same no matter where you put the brackets, so associativity. And then we have a bunch of properties of multiplication. There exists a 1 such that 1x equals x1 equals x for all x. We have xyz equals xyz no matter which way you do it. We do not necessarily have xy equals yx. Okay, but we do have and we don't necessarily have multiplicative inverses. Okay, but we do have distributivity. So we have like you can combine addition and multiplication. Okay. If all those things are happening, it is called we call it a ring. And so I'll call these kind of like optional properties. You know, commutativity, which says xy equals yx for all y and x, and like existence of inverses, which is for all x not equal to 0, there exists x inverse, such that x inverse times x equals x inverse equals 1. Okay. So rings that have all these 8 properties and like one or both of these properties are like more special. We'll give them other names. Okay. And okay. And then related to our example of the integers, we have like related constructions, which I'll say more about later, but for now we have z mod z and z, that's integers mod n. This is a ring. And the addition and multiplication is just addition mod n and multiplication mod n. And then we also have the polynomials with coefficients in the integers, which we can write like a0 plus a1x plus an x to the n, where x is an indeterminate and a0 up to an are all integers. Okay. I have 2 related examples to my example of the integers. Okay, and one more example I wanted to tell you, and that is the example, like the kind of trivial example. Oops. The trivial example is called the 0 ring. I'll write that this has one element. The one element is just the element 0. The addition is defined by 0 plus 0 equals 0. The multiplication is defined by 0 times 0 equals 0. There's only one thing, so there's only one thing to do for addition and multiplication. The additive identity is 0. And the multiplicative identity is also 0. Okay, and so in the zero ring, you have 1 equals 0. There's only one thing. Okay. But all the axioms are just trivially satisfied. Because when you multiply and add, there's only one possible result. So like whatever, if I go back to, for example, this axiom, like both sides are the result of addition. And whenever you add anything in the zero ring, the only possible result is 0. So the only possible thing on both sides is just 0 equals 0. All these axioms are just trivially satisfied because both equations just become 0 equals 0. So this is a ring, but it's kind of like not that interesting, you know. So the zero ring, we sometimes write 0 to mean the zero ring. Okay. Okay, now with those kind of examples, I mean, there's more complicated examples of rings. Maybe I'll give you one more. Example R might be the set of 2 by 2 matrices with coefficients in the complex numbers. And then multiplication is multiplication of 2 by 2 matrices. Addition is addition of 2 by 2 matrices with matrix addition and multiplication. And this is an example of a matrix that is where xy is not necessarily equal to yx. So this is called a non-commutative ring. Okay. So let us take a break for 6 minutes. And when we come back, we're going to talk about like some of the basics for ring theory. You know, just like we have to talk about subgroups, group homomorphisms, normal subgroups. We're talking about groups. For rings, we have ideals, ring homomorphisms. We have like quotient rings, all that stuff. And we also have, you know, we have isomorphism theorems for rings too. Luckily, they are very kind of similar looking to group theory isomorphism theorems. Okay, so yeah, let's break for 6 minutes and then start back. Okay, so see you in 6 minutes.